Alright, so we're just doing a quick warm-up over what we learned the past couple of days about theoretical and experimental probability. Remember that experimental probability is what actually happens, so it's based off of data. You have to perform an experiment. You have to do this for a certain number of trials. Theoretical probability is just based off of, in theory, this is what should happen. It doesn't necessarily mean it always happens. So what we're doing is we're tossing a coin, so we know we have to deal with a coin. We tossed the coin 50 times and it landed on heads 28 times. We want to find the experimental and theoretical probabilities and compare them. Okay, so what we're doing for here, for problem number 1, we're going to talk about the theoretical probability first. So in theory, for theoretical probability, all we're doing is focusing on the coin. We're just focusing on the coin. So the probability that the coin is going to land on heads is what? If I just focus on a coin itself, in theory, theoretical probability, how often should a coin land on heads, guys? 50-50, right? Half of the time, or 50%. Now, our experimental probability, the experimental probability is going to be based off of this information right here. When we're talking about our experimental probability, we are focusing on this information. So for our experimental probability, the probability of landing on heads happened how many times? How many times did we actually land on heads? 28. We landed on it 28 times out of 50. 28 times out of 50. Now, we can simplify these. They're both divisible by 2. It can simplify to 14 out of 25. 14 out of 25, which is 56%. Okay, so now when we're comparing them, if I'm making a comparison, 50% compared to 56% is less than. So theoretical probability is less than our experimental probability in this case. Our theoretical and experimental are less than each other. Okay? So let's take a look now at problem number 2. You have 5 green marbles. 2 of them are purple and 3 of them are blue. 2 of them are purple, 3 of them are blue. You pull a marble from the bag and then you record it. And then you place it back into the bag. You want to compare the experimentals and the theoretical probability. So again, this information right here, this information is based off of our experimental probability. The information that we've got right here, 5 green marbles, 2 purple marbles, and 3 blue marbles, that's going to be based off of our theoretical. So if I actually had a bag and I've got 5 greens, 2 purples, and 3 blues in there, that's how I create my theoretical information. So let's focus on the theoretical stuff first. Theoretically, what is the probability that we're going to pull out a purple marble? So how many purple marbles are in the bag? 2 of them. Out of how many total marbles that are in the bag? 10. 2 over 10, which simplifies to 1/5, which is equal to 20%. Okay, that's theoretically. If I just have this bag, I know that there are 2 purple marbles out of 10 marbles in the bag. That's how theoretical probability works. What do you have out of how much stuff you have? Experimental probability is what actually happened. How often did I pull a purple marble out of the total number of times that I did this? So first thing I would need to identify is the total. I need to know how many total times did I pull a marble out of a bag. So I'm going to add all these values together. What is 15 plus 25 plus 5 going to give me? 45. Okay, so I have a total of 45 times that I pulled this. So now I'm going to go ahead and find the experimental probability. For the experimental probability of pulling a purple. How often did I pull a purple out of the bag? 5 times. Out of how many total? 45. We pulled this 5 times out of 45, which can simplify to 1 out of 9, which is equal to 11%. So in this case, theoretical probability is greater. The theoretical probability happens to be greater than my experimental probability. We're just making those comparisons. Now remember, I showed you guys that website where the more times we performed the trials, these started to get closer to each other, didn't they? This 11% starts getting closer to that 20% until it is 20%. So remember, to get your experimental probability to be as close as possible to theoretical, or almost equal, you need a large number of trials. The more trials, the more accurate your results. Go ahead and highlight that. This information is very important to remember. You always want the largest number of trials. Always choose largest number of trials, not outcomes, not sample spaces, trials. The amount of times that you flip the coin, the amount of times that you pull a marble from the bag, the amount of times that you spin the spinner, those are trials. You always want the largest number of trials in order to have the most accurate representation. Like we said before, when you're looking to do something to yourself, like a vaccine, you don't want to do it until a large amount of trials have been performed. Okay? So how to use probabilities to make predictions. So I told you guys before, back in November, that proportions, setting up a proportion was going to be used heavily for the next few months. We're still using proportions here. We used it all last chapter, didn't we? Every single problem that you came across, you had to use a proportion. You are using a proportion here to make predictions. We call this a prediction proportion. A prediction proportion, where we identify what the probability is, and then we set it equal to what we're trying to predict. Okay, so yesterday, 50 customers bought muffins. 12 of those muffins were blueberry. On Friday, if I expect 75 customers, then how many blueberry muffins should I make? So the information that we have right here, this information is experimental probability. This is data that I have collected. Experimental probability, or information that I have collected. I know that out of 50 customers that came into my store, 12 of them wanted a blueberry muffin. Okay, so what I'm going to do is I'm going to set up the probability of 12 blueberry muffins out of 50 people. And I'm going to set it equal to what we call a prediction. You take your probability, you set it equal to a prediction. So I want to know how many blueberry muffins. That would be X. X amount of blue out of 75 people. It's just like what we did in the last unit. You're setting up a proportion to solve. Remember, when we are solving, we do our cross product first. So we're going to multiply. We're going to multiply 50 times the X to give us 50X. Then we're going to multiply 12 times 75. And 12 times 75 comes out to 900. So we have 50x is equal to 900. We then would just divide both sides by 50. And we can predict that we're going to need roughly around 18 blueberry muffins. So we're just setting up a proportion to solve. It's just a refresher, again, a reminder of what we already did all last unit and all the previous unit to that back in November and December, and then just now finishing all up of January. You've been doing this for 3 months. This is the 4th month of us doing it, and guess what, guys? We're going to do it in the next unit too. We're going to be setting up proportions to be able to solve. Okay? So proportions is an easy thing. You guys did really, really well with your proportions unit. Go ahead and go on to question number 2. Turn your paper over to the back. Let's go on to question number 2. We have a bag of fun-sized Skittles that has 2 purple, 3 orange, 6 yellow, 1 red, and 1 green. Can you guys tell which color is my favorite Skittle? Yellow. Love yellow. Yellow and orange are my favorites. Don't like the reds, don't like the purples. I once had a kid one year back in Florida who knew how much I loved the orange and the yellow, and I liked the green before they changed it to green apple. I did not like green apple. I liked it when it was lime. But he went through and he had a picture of himself with gloves, and he was emptying out bags of Skittles and putting all the purples and the reds in like a different bag, and then had jars of just the oranges, greens, and yellows, and gave me that. It was the sweetest thing.
You wrapped them with little bows?
Huh?
You wrapped them with little bows?
No, but he put them in the jars, and his mother was like, please make sure you eat these, because he spent hours going through bags of Skittles, separating them out, and here's a picture of him wearing gloves while he was doing it. It was really, really nice. It was very sweet. I had a little spoon in there, so every so often I would just take a little scoop and eat them, or I'd share them with some of the kids. It was fun. Okay, anyway, off topic, sorry. All right, so a bag of fun Skittles. We've got 2 purple, 3 orange, 6 yellow, 1 red, and 1 green. So if we have a king-size bag, so you know the fun-size bags are really small, king-size bags are a lot bigger. If the king-size bag has 150 Skittles, how many purple could we expect to see in the bag if this information stays the same, relevant, right? So you're taking the information that you know, which is this information. We know that the fun size has 2 purple, 3 orange, 6 yellow, 1 red, and 1 green. So we're going to use that information as our probability. That's the information that we know, so we're going to set that up as a probability. And our probability is focusing on what color? Purple. Our probability is focusing on purple. So how many purple does our probability show? How many purple? 2, right? We have 2 purple inside of our probability out of how many total Skittles for our probability? 13. Okay, because if we add 2 plus 3 plus 6 plus 1 plus the 1, that's the total number of the Skittles that are inside of there. 2 out of 13. That's our probability. Now we want to set it equal to our prediction. So we want to predict how many are going to be purple out of, what's the new size of the bag? 150, right? The new size of the bag has 150 of them in there. All right, so then we just do our cross products. We always multiply 13 times the x, and then we're going to do 2 times 150. 2 times 150 is going to come out to 300. So you have the equation 13x is equal to 300. You just need to divide by 13. Now, when we do that, we're going to get a decimal. Can we have a decimal amount of Skittles? No. Okay, you either have 10 Skittles, 11 Skittles, 12 Skittles. You have to make sure that you are rounding it properly. So who can tell me approximately, so that's what the wavy sign is. It's not an equal sign, it's an approximate symbol. About how many purple Skittles should we expect? About 23, right? if we round it correctly, so let's take a look at what it comes out to. When you do 300 divided by 13, you're going to get 23.076. We want to round to the nearest whole number. So that 0 tells us we're just going to leave this alone. We're not going to do anything to the 23. It's just going to stay 23. What number would that 0 have to be in order for us to round it up? A 5 or above, right? 6, 7, 8, or 9. Okay? So if it's a 0, 1, 2, 3, or 4, you're just going to leave it alone. You leave it as it is. If it's anything 5 or above, you shove it on up to the next one. Okay? So we can expect about 23 purple Skittles. Let me write that to the side. Purple Skittles. All right, for problem number 3, in problem number 3, they are already giving you the probability. They tell you the probability of pulling a red marble is 2 out of 9. So they're not telling you what marbles are in the bag or anything like that. They're just telling you that there's a bag, it has marbles in it, and the probability of a red is going to be 2 out of 9. So if there happen to be 7 reds in the bag, then how many total marbles are there? So this one's a little bit different. Instead of predicting how many reds, you're predicting the total. Okay? So it's still the same process. You're still placing your probability, which in this case the probability is 2 out of 9. That 2 over 9 means that for every 2 reds, there's 9 total. That's what a probability means. 2 red out of 9 total. You want to set it equal to your prediction. Again, the only thing that's different about the prediction is that you're told 7 reds. You need to find the total. So we put the 7 reds on top. We need X amount for our total on the bottom. And then you just solve it again the same way. You're going to do 2 times the x. That gives us 2x. You're then going to multiply 9 times the 7. 9 times 7 comes out to 63. And like before, you're going to have to do some estimation, right? We're going to have to make an estimate because when we divide 63 by 2, we're going to get a decimal. When we divide 63 by 2, we're going to wind up getting 31.5. What does 31.5 estimate to? Ian? 32. Okay, so we would say that there's 32 total marbles in that bag, approximately. Okay, I want you guys to do problem 4 and problem 5 on your own. Do problem 4 and 5 on your own. All right, let's take a look at this. For problem number 4, the table shows the number of necklaces sold in 3 sizes and 2 different metals. So you've got 12 inches, 16 inches, and 20 inches that come in silver and gold. And this is what was sold in July. He plans to sell 100 necklaces in August and wants to know how many 20-inch gold necklaces does he need to sell. So we are focusing on gold at 20 inches. That means we're focusing on that value. So when we set up our probability, currently the information that we have tells us we've got 12 necklaces that are gold and 20 inches out of a total of how many necklaces? Not 100. Out of how many total here in the chart? Tayana? 75. There are 75 total. If you take 12 plus 16 plus 5 plus 22 plus 8 plus 12, you're going to get 75 total here. So it's 12 necklaces that meet the gold 20 inch out of 75 total necklaces that they've got here. And then you want to set it equal to what you're trying to make a prediction on. So your prediction is how many out of 100 necklaces that he wants to sell. Okay, so we're going to do our cross product. We're going to do 75 times x, which gives us 75x. We're going to do 12 times 100, which is 1,200. And then we would divide them both by 75. Okay, and we're going to get x is going to be equal to 16. So he should expect to sell about 16 necklaces that are 20 inches in gold. Okay, for problem number 5, if you roll a die 21 times, we want to predict how often should we expect to land on a number that is greater than or equal to 3. Greater than or equal to 3. So I need to first focus on the probability of greater than or equal to 3. How many numbers on a number cube on this die are greater than or equal to the number 3? Okay, let's list off all the numbers. We know that there's a 1, a 2, a 3, a 4, a 5, and a 6. Is a 1 greater than or equal to 3? No. Is a 2? No. Is a 3 greater than or equal to 3? Yes, a 3 works. What about a 4? 5, 6. How many numbers did I circle? 4 out of how many total? 6. So 4 out of 6 is going to be our probability. 4 numbers on this number cube are going to be greater than or equal to 3 out of the 6 numbers on the cube. Now, we are saying, hey, we're going to go ahead and roll this 21 times, so we want to make a prediction. So we're going to set this up as x over 21 rolls. Okay, x over 21. That's going to be our prediction that we're trying to do. Here's our probability. Here's the prediction. Now we can do our cross product. We're going to multiply 6 times the x. That gives us 6x. 4 times 21.
May I have Michaela for checkout?
She'll be on her way in just a moment.
Thank you.
Okay, just wait. Okay, 4 times 21, which is 84. And then we're going to divide both sides by 6. Okay, and that's going to give us 14. So we expect about 14 times it should land on a number that's greater than or equal to 3. Okay, so that's it for our predictions. Real quickly, Michaela, before you leave, I want to go over the next page. The next page talks about fundamental counting principle and the concept of it. We don't always just have a single die or a single spinner or a single coin. Sometimes we have a combination of activities that we would be working on. And when we've got a combination, when we've got more than one activity happening, we use what's called fundamental counting principle. And the fundamental counting principle basically says, hey, how many total outcomes does this activity have? How many total outcomes does this other activity have? And let's multiply those outcomes together to figure out the total number when both activities are performed. So that's the concept. You're taking the total possible outcomes of activity A and then you're going to multiply it by the total possible outcomes of activity B. So this is actually a concept that those of you who, when you get dressed in the morning and you're like, oh, I don't really have that many clothes, I only have a couple of pants and I only have a couple of shirts. You actually have a lot of different ways that you can combine those together to create different outfits. Okay? So for example here, 8 shirts. Only have 8 shirts, only have 6 pairs of jeans and 3 pairs of shoes.
Miss French-Zheng,
Yes, ma'am.
do you still have Zarema with you?
I do.
Please send her to the clinic for a moment.
I will.
Thank you.
Okay, so here, when you've got these amounts, it doesn't look like you have a whole lot, but you actually have a ton of different outfit combinations that you can create by just multiplying. So if we've got 8 shirts, I'm going to take the number of shirts that I have, and I'm going to take the number of jeans that I have, and then I'm going to take the number of shoes that I have, and I'm just going to multiply them together, and that's going to equal the total number of outfits that I can create. 8 times 6 times 3. That comes out to 144 total outfits. You can create 144 different outfit combinations from just this amount of clothes. Okay, it's the same idea. If I have a 5-section spinner and a number cube, I've got 5 outcomes on the spinner. I've got 6 outcomes on the number cube. So if I want to do both of these together, I just do 5 times 6. How many outcomes is 5 times 6? 30. 5 times 6 means that there's 30 different ways that I can achieve outcomes. I could land on a 1 and a 1. I could land on a 1 and a 2. I could land on a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. I could land on a 2 and a 1, a 2 and a 2, a 2 and a 3, and so on and so forth. That comes out to 30 different possible outcomes that you could have from these 2 events combined together. You multiply them. You don't add them, you multiply them. Okay? Michaela, you can go if you understand that. There's IXL online tonight that needs to be completed. Okay? Out of 8 shirts, 2 are white, 3 are black, and 3 are red. So out of 6 pairs of jeans, 4 are blue and 2 are black. Out of 3 pairs of shoes, 1 pair is flip-flops, 1 pair is sneakers, and 1 pair is dress shoes. So just the same as I found my total number of outcomes by multiplying, I can find the probability of specific events by multiplying those probabilities. So the probability that I'm going to choose a white shirt, the probability that I'm going to choose a white shirt, there are 2 white shirts, 2 of them are white out of the 8 shirts that I have. So that would be 2 out of 8. I would then multiply it by the probability of choosing black jeans. The probability that I'm going to choose black jeans. There are, out of 6 pairs of jeans, 2 of them are black. So that would be 2 out of 6. And then the probability that I'm going to choose dress shoes. How many dress shoes do I have? 1. I have 1 pair of dress shoes out of how many pairs of shoes? 3. So I have 1 out of 3 dress shoes. And I'm just going to multiply those probabilities together. 2 over 8 times 2 over 6 times 1 over 3 means the probability that I'm going to choose that specific outfit combination is 1 out of 36. All right, problem number 3, the total possible outcomes of rolling 2 dice. The total possible outcomes of rolling 2 dice. I have a green die and I have a white die. How many outcomes do I have on the green die? How many outcomes do I have on the white die? And what do I do? Multiply them. So what's 6 times 6? 36. I have a lot of people who immediately think that 12 is the answer. They go, oh, I have 6 and I have 6, and they want to add them. We do not add them, we multiply. We always use multiplication here. You take that total number of outcomes of activity A and multiply it by the total number of outcomes of activity B. So you've got 6 possible outcomes for one die. You're going to multiply it by the 6 possible outcomes for the second die, and that comes out to 36 total. Okay, problem 4. What are the total possible outcomes for flipping a dime, a penny, and a quarter? So let's focus on the dime. For a dime, how many outcomes does a dime have? 2. What about for a penny? How many outcomes does a penny have? 2. What about for a quarter? 2. So now all we're going to do again is multiply them. We're going to multiply 2 times 2 times 2. What is 2 times 2 times 2 going to give us? 8. So we have 8 total outcomes. You have 8 total possible outcomes. Okay, problem 5. What are the total number of possible outcomes of spinning a 5-section spinner and flipping a coin? So we're going to focus on the 5-section spinner first. How many outcomes does the spinner have? 5. Then we're going to flip a coin. How many outcomes does a coin have? 2. Multiply them. How many total outcomes? 10. That's easy, isn't it? Very simple. Okay. You guys have IXL loaded up. You've got 15 minutes to work on your different IXL skills. 15 minutes. If you forgot your login information, I've posted that on Google Classroom as well.